Thank you. I'd like to thank the organizers first for setting up this really exciting conference with a kind of input from inside and outside that's working very well here, and I really enjoy it. So my subject is linear two-sorted constructive arithmetic, and I'd like to go slow, if I can go at all. Yes. So proofs, as you all know, may have computational content, and it is of interest to get explicit hold of this computational content, and it's well known that this, thank you, that this can be done by realizability. What is an advantage of this approach? Well, we know that programs cannot be checked for correctness, but proofs can. So if you get our programs by that approach, then we have the assurance that these things will be correct. In this workshop, which is about complexity, I'd like to concentrate on the question of complexity. That's often a criticism or possible problem of this approach, that you get programs that are very inefficient. So I'd like to tackle this kind of problem area. And there's another issue here. I would like to use constructive logic, which is obviously necessary for this kind of approach. But I want to stress the fact that constructive logic is not at all a restriction of classical logic, but rather an extension. But you may well be aware of that fact. Okay, so now let's first review a little bit what we know about feasible computation involving higher types. We've heard often in this workshop about Gödel's system T, which are finitely typed lambda calculus with structural recursion. And they are as strong as Peano arithmetic or epsilon 0 or less than epsilon 0 recursion. So from the complexity point of view, they are too strong. Now, there have been attempts to tame this complexity, and most popularly by Bellantoni and Cook, or in particular, Bellantoni's PhD thesis directed by Cook. Bellantoni used previous ideas which go back to Harold Simmons and also Daniel Levin. So he introduced essentially a system which I call LT semicolon, which is maybe called linear two-sorted lambda terms. So what is it? It restricts Gödel's system T in a way that the definable functions of that system are exactly the polynomial time computable ones. Well, this is a term system, and we all know the Curry-Howard correspondence, so it's tempting to try to extend this term system into an arithmetical system, and that's what we will do here. It's called LA semicolon for linear arithmetic, linear two-sorted arithmetic, and its aim is to solve this equation that you see there. So hiding arithmetic relates to Gödel's T, like the system we want to have to Bellantoni's LT semicolon. And again, the provable recursive function of that system will be exactly the polynomial time computable ones. Now, there is one problem in this approach. This system has to do with functions, but we would like to cover polynomial time algorithms, and that's are different things. So for instance, if you look at divide and conquer algorithms like quicksort or treesort, then they are perfectly polynomial time, but the fact in these, or the trick in these programs is that they are not linear. So how can they fit into our framework? And that's what we are going to discuss next. Let me start with just introducing or reminding you on the so-called tree-sort algorithm. It concerns lists with an L here. And so how does it work? Well, we want to sort a list. So what we do is we first convert the list into a tree. It comes next, and then we flatten that tree, and that will be the sorted list. So how do we do the tree? Well, it's called make tree here. Let me see whether I see the mouse. Yes, here it is. So the tree starts with a root. It's a little diamond here. And then how do we make a tree out of a list consisting of an element A in the previous list? So we just insert this A into the tree we constructed previously from the list. So what's insertion? If we insert A into the empty tree, well, it's a label tree. So we just take our constructor A with label, our constructor C with label A, and then it's the two branches that sits an empty tree. Now the central equation is the next one. So how do we insert A into a tree with a root labeled B, and we have two subtrees, U and B? Well, it's sort of obvious. We compare the A with B. And if A is less than or equal to B, we insert our A into the left subtree and leave the right one alone. And conversely, we do it on the other side. So now we have this tree, and the final step is a crucial one. We flatten this tree. So the empty tree is just the empty list. And how do we flatten C, B of U and B? Well, we need two calls of the flatten, and that's why the thing is not linear. So we first flatten the U, the left subtree, then we put in the B, and finally we flatten the right subtree. So the problem is we have two recursive calls of flatten, which is not allowed in our term system. The cure of that problem will be that we try to analyze this operation of flatten and also of similar other algorithms in our computation model. And this will be considered next. But before I go into that, I just would like to set up the logical framework, because it will all be about lambda terms, typed lambda terms, including derivations. So let me remind you how to build up constructive or minimal logic here. So it only uses the arrow and the universal quantifier, which are defined as usual by introduction and elimination rules. The other logical connectives, that is existential, disjunction, and conjunction, can be seen as inductively defined nullary predicates, and the A's and B's are just parameters. And then the standard axioms for these connectives are just given by the introduction and elimination rules coming from the general inductive definitions. Now we may extend this system by defining classical existence and disjunction in the standard way. So the weak existential quantifier is just not for all not, and the weak disjunction is just the usual De Morgan thing. Negation, as always, is defined to be A implies falsity. And here we are in an arithmetical setting, so we can take falsity to mean 0 equals 1. Now, what are proofs? You all know that. So we work in a natural deduction system here. So our proofs are just some form of lambda terms. And we only have implication and universal as rules. So that makes things rather easy. So we have the introduction of the arrow, where we cancel an assumption variable labeled U. And the derivation of B from A is just completed by introducing or abstracting the variable U, and you have A implies B. And as usual, we write that as a lambda term, so-called Curry-Howard correspondence, abstracting the assumption variable U in the proof term M. And then the elimination is obvious, that's just modus ponens. Now, for the quantifiers, we have to make use of a different kind of variable, namely the object variables. So for all introduction just says if we have derived A by derivation M, then we can derive for all XA if the usual variable condition is satisfied. That means we have no open assumptions involving that variable X. And on the term side, it's just the standard lambda abstraction of that variable. The elimination just does the usual thing. It specializes the universal quantifier by a term R. So the terms, object terms, are also part of that calculus. And on the term side, it's just application. So that's a very simple system. And it's nice to, or helpful to picture what terms in natural deduction, how they look like. Well, they are trees, and at the leaves of these trees, you may have object variables, x, y, and also constants, c. But in addition, you may have assumption variables called U or V of formulas A, and then we have axioms of a formula C. And then in the middle of the tree, you have the standard abstraction and application operations. So lambda abstraction on the term side, application on the term side. On the formula side, you have the arrow introduction, where you bind an assumption variable, or the arrow elim, where we do modus ponens. And very similarly, the same thing can be done for universal quantifier. And then there's a well-known realizability interpretation, or modified realizability, as Kreisel told it, which transforms such a proof term directly into an object term. And the nice feature is that the proof terms and the object terms that are used as programs later on are just in the same realm. Now, what about complexity, which is my main subject here? Let me first discuss the sources of exponential complexity, which is what we want to avoid. And I will give you two such sources. The first one is about so-called two recursions. So we define a function d, which doubles a natural number. And using this doubling function, a function e, which gives 2 to the n. So what is d? D of 0 is 0, and d of successor of n is a double successor of d of n. Very simple. And then the e is just 1 at 0, at e at successor is the doubling of e of n. So that's an exponential thing which we want to avoid. And what's the problem? What makes it exponential? Well, you see that the previous value, e of n here, is taken or is substituted into a recursion argument, the only argument of d, which is a recursive argument. So we should not do such a thing if we want to stay below exponential size growth. And the cure will be that we mark argument positions in arrow types as input or output argument positions. And the recursion arguments will always be input positions. This input-output distinction appears in Bellantoni. He uses safe and normal, and this is denoted by the semicolon in the description of the system. Next one is just the double use of higher type values. So look at the left-hand side, we can define f as a 2 to the nth iterate of d. So f of 0m is dm, and f of successor n and m is f of n applied to f of n and m. So this is a type 0 equation. It's a little easier to understand if we have a type 1 or function equation. So f of 0 is just a doubling function, and f of successor is just concatenating f of m with f of n. This gives us an exponential function. So what's the problem? Well, in the recursion equation, look at the right-hand side here, the previous value of the recursion, namely f of n, is used twice. And so that's should be avoided, and that accounts for the L in the notation of our system. So we need a linearity restriction. So we disallow double use of higher type input. Higher type output, sorry. Final thing is shown so-called marked value types, why we need them. Well, look at iteration. So we iterate a function f n times and call it f super n. And if we apply this iteration n times of the doubling function, that is another function. And if we apply it to m, we have 2 to the n times m, so something we want to avoid. Again, you can write this equation at ground type or at the function type. Let's just look at the function type side. So the zeros iteration of f is the identity, and the n plus first iteration of f is just f composed with I and f. So what's the problem here? Well, our function d for doubling has this type. I use this harpoon arrow to indicate that this n is a recursion argument. And so the type of d has this form, and when we want to iterate needs to have this type, which you see here. And how to avoid that? Well, we will only allow certain types to be called safe as value types in a recursion. So we have no marked argument positions. In our settings, this I will be admitted. We tame it in a different way than, for instance, in Cook and Capron's PV omega. PV omega is closed under substitution, but we will have a certain restriction for substitution. Okay, now let's become a little more concrete. So I'd like to set up the term system, and in the next section to set up the proof system we will going to work with. The terms are called linear two-sorted terms for obvious reasons. So what are the types first? Well, they are base types. And as base types, we just take here the Booleans, the naturals, product types, and lists. And then we have two types of arrows, the harpoon arrow and the ordinary arrow. And we call the type row safe, and it doesn't involve this harpoon or input arrow. Now, variables are typed. It's a typed system in this sense, but we need to distinguish between so-called input variables and output variables. And I do that by writing an overbar over the input variables. Now, we need constants, and certainly we need constructors of our type system, like the cons for the lists. And then we also need recursion operators. And they need to be typed, and that's a little delicate because it affects, of course, complexity. So the recursion operator with value type tau and argument type n just starts with this input arrow. Then the tau is a value at 0. And in the step case, we have the number we are at, the previous value, and gets the next value. And the whole thing returns something of type tau. And the way these input arrows and the ordinary arrows are attached here is quite essential. I've also written out the recursion over lists, which is quite similar. Just in the step, you need to have the row. That means the list item in the front and the previous list, and then the previous value and the new value. We require that this term T here, the output term, has to be safe, no input arrows. It is important later on that besides recursion, we also have the cases operator because it's a little more tolerant. So the cases operator has a similar typing like the recursion operator up here. But of course, in the cases operator, the step has no access to the previous value. Similarly for lists. Okay, so that's the basic material. And now let's look at the term system itself. It's called LT semicolon. It's built from variables and constants, as usual by introduction and elimination for the two type forms. Now, this is the definition of our term system. We have these two forms of variables of type row, input-output variables. We have the constants. And then since we have two forms of arrows, we need two forms of abstraction and application. Let's first look for the input arrow. Well, abstraction is harmless. We have just to use these overbarred variables here. And for application, we have to restrict the argument term. It should be something which is called here an input term. And the definition you see down there, when is S an input term? Well, one possible property required property is that all its three variables are input variables. And but it can be something else. So it is possible if F is of higher type that all its higher type free variables are input variables. So then if you are at higher type, the restriction only applies to higher type input variables. So that's the first definition for our input arrow. So the ordinary arrow, again, abstraction is not restricted. We take an ordinary variable here, but in application, we have to be careful. Here's the linearity comes in. So if we apply a term R to a term S, then we have to require that the higher type output variables in both R and S are distinct. So that's the linearity component in the whole thing. This restriction can be relaxed a little bit in case that our term R starts with a case distinction. So here we just require R is not starting with a case distinction operator. If it starts with a case distinction operator, we can be a little bit more liberal, which means that this T is the term of the type of iota, which and it has normally many arguments. So if you think of an if, then else, then it has a test and then two alternatives, and that can be done more generally. It is allowed that in the alternatives, higher type output variables occur in multiple forms. So here they should all be distinct, but in the alternatives, they can occur many times. The reason is simply that in a case distinction, when we evaluate it, we only first evaluate the test T, and then according to the outcome, we go in only one of the alternatives. So that's a quite important, also practically important, more liberality that we allow here. Okay, now what we want to do is we want to look at a certain computation model. Let me go back here. Yeah. And we are after polynomial time, and that means we count the number of steps in computation. So what's a computation? Well, we are working with lambda calculus all the time, so we are not going back to Turing machines, but we have a very particular computation model, which is more appropriate to the situation we are in. And that's the so-called path-stack computation model, which is, I think, sort of well known, but I still want to recall it. So what we do is we represent our terms as directed acyclic graphs, tags, where only nodes for terms of base type can have an in-degree larger than 1. That corresponds to the fact that you have computed something, you can use it many times. It's only, this multiple use is only critical if you have higher type output. Okay, so the terms of base type can have in-degree larger than 1, but it means many arrows and in a term of base type. So what are the nodes? Well, the nodes can be either terminal nodes labeled by a variable or a constant. Then they can be abstraction nodes, which means they have one successor labeled with a variable, which can be an input or output variable, and a pointer to a successor node. You'll see a picture later on when you have difficulty to imagine that, but it should be quite obvious. And the final thing is an application node with two successors labeled with two pointers. And these stacks are certainly very general, but we are just interested in DAGs that you obtain when you pass an ordinary term into such a graph, which is very well known. We need some notions here. So the size of a path stack is just the number of nodes. Then a kind of sanitary condition is that this path stack should be conformal. That means every node with in-degree greater than 1 is of base type. I just said that already. And finally, every maximal pass to a bound variable x passes only through one and the same binding lambda node. That's quite obvious that we should have that. And then there's a final notion that's called H-affine, H for higher type. That means every higher type variable occurs at most once in the DAG. So that's the linearity part of the whole thing. And with one exception, which I already mentioned, in the alternatives of a cases operator, this is not required. And we, for simplicity, identify a path stack with the terms that it represents. Now we want to have a computation model and we want to count steps. So what is a step? So steps requiring one time unit are the following. We can create a node given its label and a pointer to its successors. We may delete a node, and given a pointer to an interior node, we can obtain a new pointer to one of the successors. That means we can walk through the tree. And finally, we can test. We can test what the type is, and we can test what the label of a node is, and we can test whether something is a variable or a constant in case our node is a terminal node. So that are how we count steps. And what we want to do, we want to estimate the number of steps it takes to compute a term. That means reduce a term t to its normal form nf of t. So if you have a closed term, say of type the natural numbers, then the normal form will always be a numeral. So that's what you finally want to have. Now, as I told you, we are interested in our flattened example, in a tree sort example in lists. So let's just start with a very small observation. Let L be a numeral of type lists of n, that means a list of natural numbers. And then the number of steps it takes to normalize the concatenation of two lists. L star's concatenation, L and L prime are two lists. This only depends on L. So the number of steps, in the sense what we just explained, is just a linear function in the length of L. Now, in our particular example with this tree sort, this flatten function occurs, which you have seen earlier. So what is the number of, we need a certain size function for the flatten, or the number of steps to normalize flatten of u, that's more precise. And for that, we need something which is a little ad hoc, but can be generalized. So we use a certain special size function for numerals of this type of trees, T. And this says the empty tree has size 0. And if we have a label A and two subtrees, U and V, we count this U twice, the V once, and then we have to add 3. So this 2 here has to do with the fact that in concatenation of lists, the left-hand side counts more than the right-hand side. And using this size function, it's easy to see that if you have a numeral of type t, then the number of steps to normalize flatten of u is just linear, or big O of the size of u in this sense. Now, what we want to do is we want to show that not only all functions in LT semicolon, which is relatively easy, but including constants which are defined violating the linearity condition, something like flatten, these things are polytime computable. Now, we need to analyze these terms, of course, and things will be relatively simple when we have terms which neither contains a recursion operator nor defined constants like flatten. Flatten is a constant which is added to the calculus. So I call these RD free. So and then we also want to consider so-called simple terms. That means they do not contain higher type input variables. That was the ones where we had to look for linearity restrictions. And it's very easy to see that these simple terms are closed under reduction, subterms, and application. And simple lemma called simplicity is the following: when we have a base type term whose free variables are of base type, then also its normalization is simple. Two more simple observations on these RD-free terms. So if T is an RD-free simple term, then the path stack for the normal form of T, remember we work with terms via their path stack representation. And if this term has a size at most, this measurement here of T, then it can be computed from T in time O of size T squared. That's quite easy to see because the critical things, namely R and D, are not present. And similarly for the so-called base normalization, if we have an RD-free simple term of base type, say N or L of N, then the normal form of that term T can be computed from T in time, again, big O of T squared. And also, of course, the size of the normal form is less than or equal to T. Let me show you a picture here for that phenomenon. So what happens if we have a beta conversion where this X bar here, the input term, is of base type. Remember that these base type input terms have in degree larger than 1. So they can be referred to, or there can be arrows to this leaf of the tree from many places in the tree. So let's think we have that situation, these two occurrences of X bar in our term R, and then we have an abstraction, the lambda X bar up here, and we apply the whole thing to a term S. Now, this leads, of course, as you all know, to the normal exponential explosion that we have. But here we have this relaxation that terms of base type can have in degree larger than 1. So we just take a single occurrence of these S and then have our many arrows from all the occurrences of pointers to the X bar occurrences. So in that way, we avoid the exponential explosion. Now, the harder part of the endeavor is how to eliminate R and also D, recursion and defined constants. This is a certain lemma which is stated here. Let me read it to you. So if you have a term, Tx, which is simple in the sense we defined and of safe type, all these assumptions are needed, then you find, depending on the given term T, a certain polynomial with some properties. And the properties are as follows. Suppose you have a list R vector of safe RD free closed simple terms. Sorry for that many qualifications. And also assume that the free variables of T substituted R are output variables. Then one can, in a certain time determined by this polynomial, depending on this measure of our terms that we substituted, one can compute an RD-free term. So we can eliminate all the recursion operators and define constants, which is simple. And it's called RDF, or RD-free of T. And we need to memorize the variables X and the, and the terms R here, such that our original substituted term reduces to this one. Well, how shall one do that? Well, obviously by induction on T, and I don't have time here to go into the details. So that's done without the D part, just for the R parts in a textbook that Stan and myself wrote about 10 years ago. Literally the same proof works in our case. And here we consider this addition that we have defined constants which violates a linearity condition. And here we have just to add an additional case for the flattened constant. And this uses this lemma which we had in the beginning, that this number of steps to reduce flatten of U are in O of the measurement of U. And with these tools, we can prove a normalization theorem which has the following. Suppose you have a term T of a functional type, and these arrows may be either the input or the ordinary arrow in our term system, including the constant flatten. And then what we did ensures that this T denotes a polytime function. So that's much I need and wanted to say about our somewhat unusual computation model. Now let's do the step from the term system to the logic, or better to the arithmetic. So according to the Curry-Howard scheme, we would like to extend our term system to a linear two-sorted arithmetic. Now it's quite obvious so what we shall do. So what are the formulas? Well, of course, we have the atomic formulas for our with variables here, and then we have arrow and the universal quantifier, and they both come in two versions, with an input arrow or an ordinary arrow, and same with an input variable and ordinary variable. So the type of a formula is crucial when you do realizability. So what's the type of an A input arrow B? Well, we have this input arrow in both worlds, in the formula world and in the type world, so we can just translate it. And the same thing is done for the universal quantifier. And similarly, if we have the output arrow. And again, we have this notion of safeness, which we had for terms already, for types, sorry. Formula A is safe, its type is safe. That means it doesn't contain this input arrow. So that's quite straightforward. And now, of course, the crucial thing in an arithmetic is what form of induction do we have? Well, it's again quite obvious. So we just use input variable n bar for the induction variable, and then it's the usual thing. And we have to observe that this final arrow here is an input arrow. And importantly, this formula A has to be safe. And notice that the type, in the sense of what we had on the slide before, of the induction axiom is exactly the type of the recursion operator that will realize our induction axiom. So in that sense, things fit well. Okay, so let's now look at our example from the beginning. So apply that to the three-sort algorithm. And let's try to do that in our arithmetical system here. LA semicolon plus the constant flatten. Now, a tree is sorted if the list flatten of u is sorted. And we recursively define a function, I call it I, inserting an element into a tree E, such that if u is sorted, then so is I of AU. So that's something which you have seen before, but now it's in a more formal way. So if you insert A in the empty tree, you just use this A as a label and twice the empty tree. And if you insert A into a tree with label B and two subtrees, you do the same thing we had before, namely you compare A and B, and according to the outcome, we insert the A to the left or to the right. And using this function I, we have a sorting function for list, which just does following the empty list is the empty tree. And if you sort A colon L, then we just insert A in the sorted list. So that's, again, what we have seen before. Now, we want to do all that into our arithmetical system. And then remember, our final goal was to extract from proofs programs, and we will do that in very detail, including in implementation. And the benefit of the whole thing is that we can make sure in this setting that what we get out is polynomial complexity. Now, in order to do that, we of course have to represent these insertion and sorting functions in our logical system. And we do that here by an inductive definition of their graphs. So I write I of AU U prime to mean that the insertion of A into U is U prime, and similarly for lists. And now the defining equations that we had before turn into just some clauses of these inductive definitions. So IA empty list returns CA twice the empty list. And then we have these two clauses here with these two possibilities, how A and B relate, and then we insert, if we insert A into U, we get U prime, in case A less than or equal to B, and then we just replace the U by U prime on the right-hand side, and similarly with V on the other side. So that's the definition of our ternary inductive predicate I, and similarly for the sorting. So what would we like to do? Well, we want to derive the result of the sorting. So we want to derive that given the list L, we find a certain U such that U is a tree U, so that this U is the sorted form of the list L. Upsala. And we want to do that in our arithmetical system increased by the flatten function. Well, this is not possible. We can't do that. but we can do something which is almost as good. Namely, we can sort of do the same thing in a parameterized form. So what we can do is we take an input parameter, n, and then we take an arbitrary list of lengths less than or equal to n. And under this hypothesis, we can prove that there is a certain u such that u is the sorted form of the list L. Well, this is done just by formally proving in our arithmetical system tree two lemmas. The first one is tree insertion. So it does exactly what we just said. If we have a u with these properties like up there, then we find a u prime so that I of a, u and u prime. And how do we do that? Well, we fix an a, and then we just do an induction on n. And things are set up in such a way that this induction is possible in our restricted system. And finally, we have a tree-sort lemma, which needs a notation. So tail sub I of L is the tail of the list L of length I, if I is small enough and it's the whole list otherwise. And then the lemma says the following for L, n, and m. If m is less than or equal to n, then there is a certain u such if you take of an arbitrary list L, the tail of length minimum m and length of L, then the sorted form of that is our u. And again, you can fix L and do that by induction on m. Okay, well, I told you that this way to extract problems from proofs can be implemented, and that's in a sense quite important for this approach, because in the end you want to check that things are correct. So this can be implemented, it has been implemented. And then we have our tree insertion lemma as a formal theorem. And this theorem has a realizer, and you can extract it, machine extract it. And what you get is this term up here, which is in a language understandable to the machine, but not understandable to humans. So let me talk through that. So it starts with a recursion operator. And this is a recursion over the natural numbers, and the values are functions from trees to trees. So n is a recursion argument. And in the first case, in the zero case, you just map any u to it's a tree constructor label A and twice the empty tree. Now, the interesting thing is, of course, the step. So what you do a test whether the height of our term u is less than or equal to n1. That's the place where you are. And if that's the case, you take the first argument h of the recursion, take h of u, so you had it already. And otherwise, you make this case distinction. So if L is less than the LB is for label. So the label of U, so you compare the label A with what we previously denoted by B, so the label of our label tree, then you insert the whole thing into the left subtree of U. So I've written it down here. The label of U is, LB of U is the label, L of U is the left, and R of U is the right subtree of a tree, which is not the root. Well, and otherwise, if the A is larger than B, then you do the same thing on the right-hand side. So as usual, such terms are nice for the machine and bad for human. So let's just rewrite it as in the form of an ordinary function. And it's a function of this type here, and it's written out here again. So if we are at the zeros level of our recursion, we just take the tree just with label A, otherwise empty. And if you are at the n plus first label, you distinguish cases. If the length of U is less than n, you take the previous value of the recursion, and otherwise you have to apply the previous value of the recursion to some construct which increases the tree in this sense. Okay. That was the first lemma. Now the second lemma, slightly more complex, but not really. So that was our tree-sort lemma. Again, it's a recursion on the natural numbers, but now it gives you just one tree. It's the empty tree at the 0 case. And in the step case, you distinguish some cases. And I think this time I won't try to read this term, but immediately jump to the function here that's represented by this term. So it's a function g of this type, ln natural numbers, and then again natural numbers, oops, and values in t. So what does it do? Well, if in the 0 case you spit out the empty tree, what am I doing? And in the successor case, you check whether L is below M. That's the thing up here. And if so, you return the U, which was a parameter. And otherwise, we have to distinguish cases. So if this M equals 0, then we just take the constructor with a head of the tail from L. So U, sorry, I should tell you what U is. U is just a recursive call, right? We're defining G at L, N, and M plus 1, and U is just the previous value. And also this A, for simplicity, which will appear in a minute, is just the head of the M plus first tail of L. Anyway, it might be a little too much to grasp, but I just wanted to make clear is that the recursion equations, what you extract from this proof, is really very easy to understand. And what's even more important, it's very close to how the original proof was done. Now, if we specialize this tree-sort lemma to L and then we diagonalize again twice n, then we get that if L is less than or equal to n, then the list can be sorted. So there is a U such that SLU. And now we have to twiddle a little bit. By S bar LL prime, we express that L prime is multiset equal to L and sorted. And one can easily prove that if SLU, then S prime L flatten U. And then what we get is that if L is below n, then this list can be sorted. And this is formally proved in LA plus flatten. And the term that we have extracted from this proof represents a function which by construction is polytime, which does what's supposed to do. So h of L and n is the result of flattening G, L, N, N. And it is a tree-sort algorithm. Okay, so that's more or less the end of my talk. It's just struggling with the issue of complexity in a setting where you want to make use of this pattern of extracting programs from proofs, which otherwise would suffer from this complexity problems. Let me, at the very end, just summarize some good aspects of this approach to finding programs. I have 2 points. So first of all, which is kind of a repetition. So these proofs have to be constructive, and that doesn't mean a restriction of the classical setup, but certainly an extension if we just use classical logic in the standard way. Now, next issue was that using realizability, modified realizability, allows us to extract computational content from proofs in a very concrete way. So we can formalize our proof and then we can just push a button and we get the realizer of that proof. And finally, what I think is the most important benefit from this approach to obtain programs is that verification can be automated. When we get a certain program, we say it comes from a proof. So in a sense, we can be sure that this program is correct. But a critical person might not be satisfied if we tell this person it comes from a proof, hence it has to be correct. This person might want really to have a proof that it is correct. And in this setup, it is possible. So we can produce an internal proof of the soundness theorem. So there's a certain command in the underlying proof assistant, Minlog in this case, which just says add sound. And if you execute this command with the proof as an argument, then it gives you a formal proof that the extracted term or the realizer is indeed a realizer in the sense of what it means to be a realizer of the original theorem. Thank you. That's all I wanted to say.